Question answering system on the Stanford question answering dataset, default project implemented by Gevorg Khondkaryan. The idea of the project is to have a question answering system which works on the Stanford question answering dataset. Machine comprehension answering a query about a given context paragraph requires modeling complex interactions between the context and the query. Recently, attention mechanisms have been successfully extended to machine comprehension. In this project, I will concentrate on reading comprehension and question answering. For majority speakers, the goal will be to answer questions correctly, and majority will agree on both provided question and answers, and won't contain irrelevant information. As a data source, as mentioned, I am using Stanford question answering dataset version number 2. The dataset contains more than 150,000 question-answer pairs taken from the Wikipedia dataset, and to answer every question will be a segment of text or span from the context paragraph. The leaderboard on the SQuAD website shows many deep learning models created for this dataset, and many researchers have came up with different architectures. From the leaderboard, the best scores are achieving the models which are based on the BERT with pre-trained data, and the BIDAF models are giving more creativity in the implementation time. For this project, the official Stanford question answering dataset version number 2 will be used. It has 3 splits: train, dev, and test. The train and dev sets are publicly available, and the test set is entirely secret. The structure of the data consists with the article, paragraph which is related to that article, and question-answer pairs which are related to that paragraph. For this project, 3 approaches were taken: BERT, BIDAF, and SQuAD. BERT model architecture, which stands for bidirectional encoder representations from transformers. BERT is designed to pre-train deep bidirectional representation by jointly conditioning on both left and right context in all layers. The pre-trained BERT representations can be fine-tuned with just one additional output layer to create model for question answering system. BERT's model architecture is a multi-layer bidirectional transformer encoder based on the original implementation described in Vaswani. BIDAF, bidirectional attention flow, it's a hierarchical multi-stage architecture for modeling the representations of the context paragraph and different levels of granularity. BIDAF includes character level, word level, and contextual embedding, and uses bidirectional attention flow to obtain a query-aware context representation. SQuAD, combining local convolution with global self-attention for reading comprehension. The high-level structure of the model is similar to most existing models that contain 5 major components: an embedding layer, an embedding encoder layer, a context query attention layer, a model encoder layer, and an output layer. To evaluate the models, 2 metrics will be used: the exact match score metric, which indicates whether there is an exact match between the prediction and the ground truth, and the F1 score, which rewards partial matches between the prediction and the ground truth. We'll choose model parameters, which are maximizing the F1 score on the development set. My best result with BIDAF-based models was with BIDAF with char embeddings with self-attention. On dev, the set, the exact match score was 62.84 and F1 was 66.26. On a test split, it was 61.3 and F1 score was 64.77. Here you will see all the results from the models that I have trained, which were BIDAF baseline, BIDAF char embeddings, BIDAF char embeddings self-attention, BIDAF char embeddings with multi-head attention, SQuAD, and BERT. Comparing the results, BIDAF char embedding gave me about 2.2% improvement about baseline over F1 score. BIDAF char embedding with self-attention gave me about 3.1% improvement above baseline over F1 score. I analyzed randomly selected 200 examples, from which 78 has errors. I categorized the errors. So one of the category was non-precise answer boundaries. About 90% of errors falls into this category. syntax ambiguities plus totally wrong answers, which were around 57%, and predicted as NAs about 24% error. For this project, I have re-implemented the BiDAF layer, adding also self-attention layer. I showed how important was attention because it increased scores comparing with baseline. I also trained BERT and QANet. I didn't have much improvements there because fine-tuning process faced with memory issues, especially increasing byte size immediately, giving not enough memory issue in GPU. Overall, I am rather satisfied by the model as it has achieved good results. There are still many improvements to be made, and I have trained with no such many tuned hyperparameters. My approach was to train with different models. Here are some important papers for this work. The first one is a SQuAD paper, the second one is a BiDAF paper, and the third one is attention all you need the paper. Thank you for your attention and for a very good course. Thanks.